problem that's comparable to an SMO Junior problem back in 2012. And I think it's useful here to think of b as an integer, although maybe not necessary, but it's usually on these kind of problems it works out where these coefficients are integers. Now we're supposed to the roots are understood to exist, and we're supposed to find the minimum value of the difference of the roots quantity squared. Kind of an interesting problem. So what we do is just carry on here in a fairly predictable fashion. If you expand this out, you get x squared minus the sum of the roots, and this is a very well-known result referred to as Vieta. And again, this can be obtained just by dumbassing it, just multiplying it out. Okay, so x, and then the product of the roots, since the minus signs cancel, is the constant. Okay, and so again, what's useful about this is that the product of the roots and the sum of the roots is visible as coefficients of this second degree polynomial. Now again, we're supposed to find this value, and so what we can conclude by equating coefficients minus the sum of the roots is the coefficient of x, but 2b, you see, 2b is the coefficient of x in the original problem, right? And so that's where we get these two statements right here. And also b minus 9 would be behaving as the constant. That's why we can set r sub 1 times r sub 2 equals to b minus 9. Okay, so kind of nice to see that. And again, that's referred to as Vietas, something you can discover on your own without even knowing it has a name. So now another important result here that allows us to take advantage of these assignments is that the difference squared is equal to the sum squared minus 4 r sub 1 r sub 2. The reason being is minus 2 r sub 1 r sub 2 is present when you expand this. I won't write it out, but it's very clear that minus 2 r sub 1 r sub 2 happens when you expand what we're looking for out. Okay, and so that a plus 2 would happen in this one, right? So plus 2 r sub 1 r sub 2 would happen here, right? So that explains why we end up with minus 4 r sub 1 r sub 2 right here. Okay, now the rest of it is just very straightforward. You can factor a 4 out of this expression to end up where at this stage right here, 4 times 9 being the 36 that you see right here. Now, y'all, this piece right here is a result of completing the square. And let me write down b minus 1/2 squared. Let me just write it off to the side. B minus 1/2 squared. It's a standard idea of taking the coefficient of the linear term, okay, and then dividing it by 2. And then when you expand this out, you get two of the terms. You get two of the terms of interest. You will get b squared minus b, right? Because minus half plus minus half is the whole, right? So you get b squared minus b. All right, but we get kind of an unwanted constant. We have plus 1/4 also, right? So you see that explains why this piece right here is actually equal to 9 minus 1/4. Okay, see that way you take care of this annoying constant. This annoying constant bought us something because it gave us b squared minus b, right? But then we have to subtract it off to maintain the equivalency of this statement. Okay, so 9 minus 1/4 certainly is 36 over 4. Minus 1/4, right? 36 over 4 is the same as 9. Okay, so what we can conclude right here, folks, is the minimum happens when b is equal to 1/2, right? 1/2 makes the expression as small as it can be, all right, but then the value of the expression would be 4 times 35/4, which is equal to 35, okay? Which is the answer, which is the solution. Again, a fun problem. It's a junior level SMO competition problem, okay? And I like it a lot because you have to complete the square, take advantage of equating the coefficients, okay? And also, that's about it, just some algebra and some substitutions, basically. So anyway, find the minimum value of this. It's actually equal to 35. Hope you liked it.